We're looking at reasoning with probabilities, so we're going to examine rules for using probability, how to calculate certain outcomes, and this is significant for philosophy because of how it fits in with argumentation and reasoning. So a few preliminaries and context here. First of all, of course, when we're reasoning with probability, we need some basic math skills, especially working with fractions. And so if you need to review that, you definitely should do so. And I'm sure there are plenty of helpful videos on Khan Academy and elsewhere to help you do that. In fact, I'm sure there are other helpful videos on reasoning with probability through math professors. All inductive arguments involve probability. So it's built into our definition of what a strong inductive argument is. And so we have some inductive arguments, a subset of those, that appeal explicitly to probability, use numbers in the reasoning process. So again, to quick review, a strong inductive argument is one such that if the premises are true, then the conclusion is probably true. So we have with inductive reasoning, we have this level of probability that we are using. And if we can be more precise with that and have data and use numbers to reason with, then that makes it all the more clear what our argument is doing and to what degree we should believe the conclusion. In fact, the degree of strength for evaluating inductive arguments would be determined by how probable the conclusion is, given the premises that are provided. There are different uses of probability in a wide variety of contexts. One use is to identify the ratio of favorable to possible outcomes. Now, by favorable, it could mean the outcome that we're investigating, the one that we're concerned about. So it doesn't always have to be something positive in the sense of beneficial, but it could be. So it's the type of probability involved in gambling, including buying a lottery ticket. So that would be a case where you want it to turn out a certain way. So one or more outcomes going to be favorable or preferred, while other outcomes are possible. Now, this is the primary way we use probability in inductive reasoning. We have ratios then, the ratio of favorable to possible outcomes. And again, here, favorable, think of the outcome that we're investigating. How likely is it? And so it could be even something like exploring the probability that one might get cancer given a certain amount of evidence. And so that would be considered the favorable outcome that we are exploring, although obviously no one wants cancer. Another way of thinking about probability is the frequency with which events of a certain type occur. And this is the type of probability that we use in actuary tables. So we use this to calculate how much to charge for life insurance. It would also apply in other kinds of insurance as well. So for example, an actuary table would give us the ratio of deaths of those currently 50 years old over the next 40 years. So you just gather all the data, you have your table, and you're using probability to calculate these outcomes. The number of people who will not make it through med school out of those who start med school, that would be the frequency of that events of a certain type occur. So we've heard the adage, look to your left, look to your right. One of those persons won't be here at graduation. And those kinds of information, that kind of information can be helpful. The third way you might use probability is to calculate the degree to which it is rational to believe certain statements. So this is the type of probability involved in sports betting. To what degree should one think that the Cubs will win their next game, right? But it's also much more important, at least in my mind, than that. It's very relevant for a wide variety of philosophical issues and other contexts. To what degree should we believe an argument's conclusion, right? Measuring the degree to which it's rational to believe something is also significant. Again, it's that first type of probability that we will be focusing on, the number of favorable outcomes given the number of possible outcomes. Now, just a word of caution here regarding probability. When the situation is very simple, say a coin flip, right? We know there's 1 out of 2 possibilities, heads or tails. Sure, we can do fine in that situation, 1/2. We may even be able to do it, calculate the probability of getting 2 heads in a row in our head and understand that that's going to be 1/4. So we can do okay with very simple situations, but as probabilities get more complex, we're just really bad at doing this. We're really bad at estimating probabilities in complex situations. And so even well-educated and intelligent people often make significant mistakes when estimating probabilities for complex situations. So for example, a study was done where they gave doctors certain information about a test and the validity of the test, how likely it's going to give the correct response, and then gave them information and asked them to calculate or provide the probability that something would be true. And they were just terrible at it. They were just really bad at it. And these are doctors who are intelligent, obviously well-educated people. So all of us can be pretty bad unless we think through carefully some rules that we've figured out. And that's why probability calculus is so important. I hesitate to use the word calculus. It's not calculus in the typical sense of math, but it is a system by which we can calculate probabilities. And that's what we need in order to do this. So how do we measure probability? Well, we measure it by a number, right? We assign numbers that indicates the probability of something. So the probability that a hypothesis H is true, given certain evidence, and we abbreviate that E, is equal to a number. We're going to get a number. So you want to know how likely it is that something is true, that something is your hypothesis, given some information, that's our evidence, and then we assign that a number. And that can be expressed in shorthand. We use the PR for probability, the H in parentheses is the hypothesis, and that's going to be an N. Or we can include the probability of H with that vertical line E. That means given evidence E equals N. N is just a number. So an initial example here of what we're talking about. Suppose you want to know the probability that a student attending WIU, Western Illinois University, is from Illinois. Well, your hypothesis in that situation would be the student is from Illinois. That's what you are investigating. You want to know to what degree that is likely. Well, your evidence in this case, the E that is assumed here in our situation is the student is attending WIU. So how likely is it that we have somebody from Illinois, given that we know that they are attending WIU? And in that case, we can go to the WIU fact book, and this may be pretty old data, but in 2018, it says that 7,447 WIU students were from Illinois out of 8,502 who were enrolled. And so you do a little math there, and that tells us that N is going to be 0.876. That's the probability. All right, that 876 may not mean too much, So let's think through this a little bit more. The first rule, right, is that your n, whatever it is, when you are identifying a number, assigning a number to probability, it must be a real number between 0 and 1 inclusive. So 0, 1, 0.5, 0.333, those are appropriate numbers for measuring probability. But 1.2 or negative 0.5 or 3 are not. Those cannot be used ever for measuring probability. It does not make sense. So 0 is the number assigned to something that is not possibly true. So the hypothesis that I will someday play for the Chicago Bulls. What's the probability of that occurring? 0. It is not happening. 1 is the number assigned to something that is a sure thing, or close enough to a sure thing not to worry about it not happening, like the sun coming up tomorrow, disregarding whether clouds are present or not, right? As we know, tomorrow is another day. So we would assign that a 1, right? That we just know that it's going to happen. All right, let's just consider a brief, short example here. What is the probability that a 6 shows on a single roll of a fair die? So you have 1 die you're rolling, that is 1 out of 6 opportunities, probabilities, 1 favorable outcome, getting the 6, 6 possible outcomes. And so we can convert that and put that into a decimal form, 0.167, which is, of course, a number between 0 and 1. So that makes sense. There's only one way to get that favorable outcome, either, right, by rolling a 6, the number of possible outcomes 6. So that's how we calculated that number. All right, rule 2. And we'll have 4 rules, and then we'll include a theorem. If H, the hypothesis, follows deductively from the evidence, then the probability of H, given E, is 1. So if your evidence includes or deductively implies that H is true, then you have a 1. So given the evidence that the cat is living in the house, the probability that the cat is living is 1. And it's a guarantee. If you know the cat's living in the house, you know the cat is alive. So that would be a case of a 1. So we've already talked about that. So rule 2, very simple. Rule 3 is very helpful in a variety of situations. So we have 2 things that we are considering. If 2 sentences, 2 hypotheses, H1 and H2, are mutually exclusive, which of course means that the 2 hypotheses cannot both be true, then assuming the same evidence in both cases, the probability that their disjunction, that is H1 or H2, is true, is equal to the sum of their individual probabilities. We can express this formally in this way. So we have the probability of H1 or H2 given our evidence equals the probability of H1 given that evidence plus the probability of H2 given that evidence. So let's consider a case where we apply this, and our evidence is going to be that we have a standard die that is rolled once. So what's the probability that the die lands with a 2 showing or a 3 showing? Now these are mutually exclusive. We're only rolling the die once. We cannot possibly have both a 2 or a 3. So this fits our situation for rule 3. We can add these probabilities, and the individual probabilities are 1/6. So 1/6 plus 1/6 equals 1/3 or 0.33. Note again, the 2 hypotheses cannot possibly both be true, right? The die is only rolled once, and thus it can only show one number. That's what the kind of situation we need in order to use rule 3, where we are adding their probabilities together. Rule 4 is a situation where we're looking at a conjunction. The probability of the conjunctions of two sentences is equal to the probability of the first sentence multiplied by the probability of the second sentence on the condition that the first sentence is true. So when we're looking at our second sentence, we're assuming the first one is true. It has to be true for both of them to be true, right? So rule 4 applies when calculating the probability that the first hypothesis is true and the second hypothesis is also true. So we can express this formally in this way. We have the probability of H1, that's the first hypothesis, and H2, given our certain evidence. That's the same as, that equals the probability of the hypothesis given the evidence, multiplied by the probability of our second hypothesis given the evidence and given that H1 is true. So here's the kind of situation we're talking about. The probability of rolling a 4, then a 6, that is, we're using one die, and we first get a 4, we roll it again, and then get a 6. So we have 2 consecutive rolls of a die. So that's going to equal 1/6 times 1/6, which of course is 1/36, or converting it to decimal form, 0.0278. If you want to think about that as a percentage, that would be nearly 3%. Not very likely. Now, you've noticed that when we are using fractions, I've converted that to a decimal number between 0 and 1, of course. And when calculating probabilities, we always convert fractions to decimals. That just makes it easy. That's my preference. And then once you do that, you round off to the nearest 3 significant digits. 3 is enough for most purposes, and you go farther than that, and it becomes rather insignificant. And so, for example, you calculate the probability as 0.003486. Well, we could just round that off to the nearest 3 significant digits, and the answer would be 0.00349 in that situation. Or another example, if the probability is 0.30004, we'll just round that off, and that can round off to 0.3. Again, it's just much easier to get a grip on it when we are doing that, when we're limiting it in this way. And of course, we want to convert fractions to decimals so that we always have that clear number between 0 and 1. So if it's 1/3, you would state the probability as 0.333. Again, we're rounding off to the nearest 3 significant digits. Okay, one other theorem to add that will be useful. So we have an important theorem here, and that's if the probability of our hypothesis given the evidence equals n, then the probability of not getting the hypothesis given the same evidence equals 1 minus n. Now that can be very important in certain situations. This theorem is very helpful in situations of inclusive disjunctions. That is, situations in which the favorable outcome involves one thing or another occurring, and they could both occur, right? So this is unlike the situation for rule 3 where they were mutually exclusive. In this case, they are inclusive. We could both occur. So how do we apply the theorem? Well, it'd be useful in a situation where you're asked what's the probability of getting a 4 or a 6 when rolling a pair of dice. So here we're rolling 2 dice at the same time, and we're asking how likely is it that we get a 6 or a 4? Is there a 6 or 4 showing on either dice? In this case, we cannot use rule 3 the situations are not mutually exclusive. One of them could be a 6 and the other one could be a 4. And so we cannot use rule 3. So this is a situation where we need to use the theorem. And in order to use the theorem, we're going to need to know the probability of not getting a 6 or a 4 on both rolls. So we want to calculate that. Well, if you're not going to get a 6 or a 4 on the first die, that means you're getting a 1, 2, 3, or 5. And that is 2/3. That's 4 out of 6, or 2/3. And similarly for the second one. And so we multiply 2/3 times 2/3. And of course, that's 4/9, or we put it in decimal form, we have 0.444. Now, keep in mind, we're not done here because that's the probability of not getting what we're interested in. But now we can use the theorem. Now we can use the negation that we just calculated, not getting a 6 or a 4, and we subtract it from 1. And so we have 1 minus 0.444, and that is 0.556. And so that is our probability of getting a 6 or a 4 when rolling a pair of dice. Again, even now, even at this stage, it's probably getting to the point where you may not have estimated that as, nearly 50%, right? It's 55.6% chance. And if you were estimating that, that may not be in that same range. So already, fairly simple situations, we see why thinking through probability calculus is going to be helpful in a wide variety of situations.